Hello everyone, welcome back to the open class. So I'm Desire, and today we want to build on what we have been doing, which is trying to first subscribe to LiDAR data so that we can be able to make our robot be able to perceive the environment, see the things that are in front of it, to the left, to the right, using LaserScan data, right? So from the most recent class that we did, we also learned how to create a publisher for command velocities, right? So in order to work with LaserScan data, we have to subscribe to the LiDAR topic, and then in order to move the robot, we have to publish onto the command vel topic. For our use case specifically, when we are working with the board box, we have namespaces, so it will be fastbot _1 and / command vel, right? So let me just do a couple of checks to make sure you can all hear me, and also begin to share my screen. So all right, I can see this one is working correctly. Let me just check real quick here. So audio check, can I get a confirmation? Is the audio alright? Can you at least see my screen at the moment? Okay, Sonia says hi. Alright. And okay, so what we're gonna do is, as always, when you do open classes, we're gonna fork the ROSJECT so we can open it, and you will also have a copy of the ROSJECT for your use or for reference, so that when you want to come back to this open class to see what did we discuss and what other nitty-gritty points that you want to pick from it, you can also do that. So I'm gonna click here where it says fork and open the class ROSJECT, so that I can also have a copy. So I'm gonna do that now, and I will run it. Let me, okay, so I have the chart here, just give me one sec. Alright, so as we wait for it to load, let me check real quick if I have a current running one. No, not at the moment. Alright, so I'd like to know if we have all managed to fork the ROSJECT. If we have, you can just put thumbs up or say yes, we have. And how is the latency? Alright, so this is gonna be loading, and let's just see what the notebook looks like. Okay, so okay, 1, 2. Alright, the notebook is loaded, so that's good. We can start at least using it to see some of the stuff that we're going to be doing. Alright, Hello, Yuhong. Thank you. Okay, so um, basically, when the simulation is loaded, you should be able to see something like this. So you should be able to see people in the simulated environment, and if you zoom from the top, you should be able to see the robots. So let me just check if mine is loaded, and then we can. Yeah, okay, it's taking a bit of a while, but no worries, it's going pretty quick. So when it loads, you can click on it and then use the mouse to drag so that you can zoom in. For example, you can get closer here and then use to your mouse to get the top view so that you can see the robot like this. So the one that we're going to be using for our purposes is this one, the red one, Fastbot 1. So this is the one that also is publishing to all the topics that have got the namespace Fastbot 1. So if we go into our terminal and we just run ROS2 topic list, once the simulation is loaded, we should be able to see all the topics, right, including those for Fastbot 2 and for Fastbot 3. So on the basis of what we did from the previous classes, let me say, so we did a LiDAR data subscriber, and we also did a publisher for command velocities, right? So what we want to do in this class is to bring these things together so that we implement some form of a not really intelligent behavior, but you could call it that way, but some kind of feedback loop where the robot can move and stop relative to the kind of data that it's receiving, right, via the LiDAR topic. So if it sees that there's an obstacle, right, it can stop or change course, right? This is what we going to do in this class. This is what we going to try to understand. How do we do these things? How do we combine publishers and subscribers in the same node, right? So you're going to see that the code that we're going to use is very simplistic. At the same time, it's going to also help us to understand why is it advised to implement it slightly differently, because as you see when we go into more detail, that you hardly have got a callback, right, a LaserScan data callback, or we call it a scan callback in this node. You hardly have got a scan callback that also does publishing in itself, right? So this is what we're gonna be doing. This is what we're going to be using. However, I want to make a very strong point that standard practice says you're supposed to separate the two and create a timer so that it takes a responsibility for controlling how often the command velocities are being published. So we're going to get into detail about this as we go on, but for the purposes of beginning this class, we want to see this code in action. We want to see how do we implement something of this nature. How do we implement a node that does or that allows the robot to exhibit this behavior? Okay, so let me just check real quick if our simulation is loaded. Right here. Okay, we're still going. Alright, but in the meantime, what you're gonna do is we're going to go on and try and create our package, right? So as we always know in ROS2, for you to create a node that does something, that node has to be implemented in a package, right? So you always create a package, even when you do the creation of custom interfaces, for example. So let's say you have your own messages that you want to implement that are not implemented in ROS2 or even ROS1. You also have to do that in a package, right? So what we're going to do is we're going to create a package where we will put our obstacle avoider a node, right? So the node that will enable our robot to move, use LiDAR data to see that there's something in front of it and stop. And then we're going to also break down the code bit by bit. So let me just run through the list of things that we're going to do in this class as we always do. So the first thing that we're going to do is create a package, as I've said. and then we're going to create our obstacle avoider.cpp in the SRC folder. So I will go step by step and do it in the terminal as we always do, and it is also standard practice for us to have this level of competence where we don't necessarily need to be using the IDE every time, right? So I will be doing that, and we're also going to review in more detail where our subscriber is and where our publisher is and where we call each and at what frequency is each of them being called, right? Because if you remember what I've said earlier on, that we have combined in this, for the purposes of this class at least, we have combined our subscriber and publisher, but that is not standard practice. I've said it's very important for us to understand, but for the sake of simplicity and for easier reference with regards to our class at the moment, it will suffice, right? So it will make our robot at least do what we want in simulation, and then we're going to also try to run the same code on the real robot, see where it fails, try to make some changes to see if it gets us to the behavior that we want, right? And I'll be highlighting the different ways in which you would want to do it when you're now doing it for more complex systems, right? So that is involving, i.e., separating your publisher and subscriber if you want. Otherwise, some systems you cannot do that. You have to have the two within a same function, but then those are special conditions, right? And we also are going to speak a bit about why do we need to use a timer in the event that you want a different frequency of publishing command velocities versus one that is dependent on the frequency at which your LiDAR data is coming, right? Okay, so we're also going to create a launch file, right? And our launch file is one that will enable us to launch our node. So if you'd allow me to highlight this a bit, yes, is one that will going to allow us to launch our node and see it running, right? So you probably know by now that there are two ways you can run ROS programs. So you can either do ROS2 run. In that case, you don't need launch files. But if you want to use ROS2 launch, where you are launching maybe even multiple nodes, right? That's the advantage of using launch files. Then you have to implement a launch file for the nodes that you're going to be running or that you want to be spinning when your whole package or program is running. Then we're also going to do some modifications to the CMake list file. So we're also going to explain a little bit about that, so we understand that this is standard procedure every time you're developing ROS2 programs or ROS1 programs, even though they are variations in how you do it. But for the purposes of ROS2 that we are mostly concerned with in this class, we will speak about the modifications in detail as they should be, right? Then we're also going to compile a package and then run it to see it working, as always. Okay, so real quick, let me just check our sim. Okay, it's getting there. All right, if anyone has managed to load the simulation, you can put a thumbs up or whichever works for you. All right, so let me check real quick here. Alright, so I'm going to open out our terminal and we're going to start creating our package as we wait for the simulation to load, and then just go step by step, right? So as always, our packages are created in the SRC folder in our ROS2 workspace. So if I do cd to open the ROS2 workspace and I list what is in there, you see there is a build, install and log folder. But these are there because I've previously built some packages here. However, for your case, you may have them or you may not have them, but I'm going to assume that you have them as a result of the one package that we'll see is for the simulation, right? So we're going to also open the SRC folder, right? in the SRC folder that is contained, it's like source folder that is contained in your workspace that we call ROS2 workspace in this case. It can be named differently. However, for ROS2 and for us at the Construct, this is how we name our workspaces. You would probably have like workspaces that have custom names depending on what you're doing. So if you list the contents of the SRC folder, you will realize that I've got obstacle avoidance package because I've created one before. However, you should have these two yourself, except this one, because we're going to create this one. So what I will do is I'm going to remove this myself so that we can create it together. Okay. And okay, so give me one sec. Okay, so we see that it's gone, right? So we cleared our terminal, and this is what we should have at the beginning, right? So in this source folder, this is where you create all the packages that we use. So you may have more than one package that you are creating. You may have more than one package that you want to run on your project, for example. So you may have a package for a custom interface, as I said earlier. You may have a package for an obstacle avoidance behavior, for example. You may have a package for something completely different, but the idea is that in this folder here that we call the SRC folder that is contained within the workspace, this is where your packages are, and they should be there actually is standard practice. So we're going to create our package, and we want to break down this command for creating a package. So as always, to reinforce those fundamentals, it is very important for us to make sure you understand what you are doing when you call ROS2 create, and what is it that you see here in this command that we see here, right? So you can copy it by clicking here. However, I like using Control A and then Control C, because you don't have maybe some foreign characters introduced depending on what's happening with the copying system. So if you do that, and give me one sec, and you go in your terminal in this RC folder as we've been doing, and then you Control V, right? So here we are calling the command ROS2 package create, right? So this is the command to create a package, and then next to it we put the name for the package that we are going to create. So in this case, our package is going to be called obstacle avoidance underscore pkg, shortcut for package. And then we have this you could call it an option or a flag, right, that is responsible for specifying what type of package you're building. So for us, because we're using C++, we have to specify amend CMake as the type of package that we're going to build. This will make the ROS2 framework be able to recognize that, okay, there is a C++ package that's being created, and it will add the necessary things for that package to be built, i.e. the package XML, the CMake list. They'll be added as in their default state, right? So you need to make modifications to them. However, you will have other things done for you, right? So we're going to see that as well. And then we have dependencies, right? So this specifies what your package that you're building, what it will depend on, or the kind of libraries, ROS2 libraries that will depend on for it to work, right? In this case, we have RCL CPP, which is basically the library that makes the ROS2 C++ client be available for use, right? So when we call include, for example, in our obstacle avoider node, right, when we call include RCO.cpp, and when we now inherit from the node class itself, right, it's made available as a result of having included the RCO.cpp as a library. And then we're also going to include geometry messages package, right? So this will enable us to be able to publish command velocities to a robot after we have we have figured that the front is open, for example, let's say, right? And then we are also including sensor messages package, right? So this one is here to allow us to, let me say in general terms, to subscribe to our LiDAR topic. That's the first _1/scan, right? And be able to process that data, right? So I'm going to press enter, and we're going to see our package be created, right? So, and if we list now the contents of this directory, right, you will see that now you have got obstacle avoidance package in there. And if you open that using the cd command and you list the contents of that, you will see that you have now a cmake list.txt. You also have an include directory in there. You also have a package.xml, and you have the src directory in there as well, right? So these are the things that are made available for you as a result of specifying that you want the C++ package to be created. Then the ROS framework knows, okay, I need to create and include directory in that package. I need to the package XML is there in all other packages. However, the structure of what the obstacle avoidance package will contain is very much dependent on what type of package you're building, right? So then you will have src directory also created for you there. So in this directory here, the src directory, this is where we will create our cpp files. So all implementation files will go in this directory. However, if you have header files, for example, and you want to separate implementation and interface, right, by using headers and implementation files, then you have to put your header files in the include directory, and then you will put your implementation files in the src directory. So for us, we're not using any header files, so we're going to be using the src directory for most of our work. So let's just check real quick if our simulation is loaded. Give me one sec. Yep, it is loaded. So you must see something like this when your simulation is loaded completely, and then we will navigate to a top view, planner view, so that we see which bot we are manipulating and what it's doing, right? So let me just check some few things real quick. Okay. All right, so if you click in that simulation window and you drag, right, you should be able to rotate it so that you get to see the robots from the top, like I've done here. Then you can zoom in to see the robots. I'm gonna rotate it a bit so that we see them in this perspective, right, as they are shown in the notebook, right? So let's go on continuing creating our package and trying to understand the things that we're doing. So after you have created your package, you will also have to create an obstacle avoider.cpp in that src folder that I've spoken about. So I'm gonna do it with you here. So let's go. Alright, so if we open the src directory, right, and then we list, right, we're gonna see that src folder that is contained in our package is got nothing at the moment. However, as I've said, this is where we want to create our obstacle avoider .cpp, right? So to do that, you use the touch command, right? So touch, and you specify the name. So we call it obstacle avoider.cpp, right? And then you hit enter. Then your script is created, and you can check by listing the contents of that directory. You see now we have obstacle avoider.cpp, right? And then after we've done this, we are going to add our code via the IDE, right? So you can find your IDE here on the two angle brackets here. It's if you hover your mouse on that, you see that it says code editor. That's what we're going to use. However, you can also make modifications to these files in the terminal. It's going to be tedious because you can't just copy and paste like that. There are some special things you have to do, but it's a good thing to know that you can do these things, right? So if you type in vim and you put the name of the file, in this case it's obstacle.avoid.bash, you can see that the file is empty, and you can make modifications to the file by pressing I for insert, right? And then you begin writing. Maybe in this case we're gonna say include, for example, right? Include for example, geometry MSGS. That's the first statement we have in our file. However, for the sake of speed, in this case, we are not going to use this way of modification of changing or adding contents to our file. So I'm just going to hit escape first, and then you press colon, then Q, small q by the way, to exit. Then it's even prompting me to say, do you want to override the changes we've made? So if it does that to you, you just say escape again, and you push the exclamation mark. Just give me one sec. Right, so colon, right, so escape, colon, and then you hit Q, and then you add an exclamation mark. It must allow you to exit. Yes, because you're saying, yes, I want to do it that way. I want to quit, right? Despite that I had made some changes, right? Now, let's open the IDE so that we can add the contents of our obstacle avoid.bash. So if you click here where it says code editor, you will see your IDE open, right? And if you open your workspace, go to the SRC directory, go to your package, obstacle avoidance package, and in its SRC directory you can see that you've got obstacle avoider .cpp, right? So the reason why I was emphasizing doing things in the terminal is sometimes when this tree is confusing to you, if you go to the terminal and you open the directories, that confusion can be cleared out by simply going step by step into each directory and knowing what is there, which one should I go to next if I want to make modifications. That's why I like this approach, and it's also a good thing to know, because sometimes it straightens things in your head when you're dealing with very complex systems, right? So now we're going to copy the contents of our obstacle avoider, right? And we're going to add them to our empty file here. So I hit Control A, then Control C, and then I'm just going to press Control V here. Then we save, right? And we have our file here. So let's talk a bit about what's going on in this file. So I'm going to make this full screen, and we can talk a bit more about what we are trying to do, why we're doing it. And give me one sec here. Alright, so our obstacle avoider node, right, it inherits from the node class, which we've got here. So this is what I was saying when I said you need to include the RCO-CPP library, because it makes this node class available, the one that you inherit from when you are creating a custom node, right? In this case, we are creating a custom node that we call obstacle avoider, right? And our node is it's a class in C++, right? So, and we call that class obstacle avoider, but it inherits from the RCO-CPP node class, right? So it's in the RCO-CPP namespace. That's why you see this colon here, and then you have got the node class that you're inheriting from, right? And here we have got various include statements. So the way we make this node class available is by including the RCO-CPP client library like that, right? We also include the geometry messages twist header, right? The one that you see at the very beginning here. This is the one that allows us to get the what can I say, the ability to send appropriate messages that are going to drive our robot. So they are sent as twist messages. That's why you see here you have to declare that I want a twist, an object of type twist, right, which is found in the message class of the geometry messages, let's say header, for example, right? And then you have sensor messages here. You are including this because you want to have this here that you call, so we pass it as a template parameter because we are creating a subscription to a subscription for LaserScan data, right, that will subscribe on the topic that we call fastbot_1/scan, right? So this is our subscriber here, right? This is our subscriber that's being created in the constructor, right? So this is a constructor here in C++. So something that has got the same name as the class, but it's got parentheses next to that name, right? This is our constructor, and then we also initialize the class it is inheriting from. So the class above it, we initialize it and give it the name obstacle avoider, right? And then we are also creating a publisher, right, in the same constructor. So the constructor that creates our obstacle avoider node, right, also initializes an object of type a publisher, let's say, right, with the template parameter twist, because we want this publisher to publish a message of type twist, right? If you wanted a publisher of a different type, this would be different. The highlighted part would be different. You would be publishing maybe imagine that you want to publish an object of type, a message of type LaserScan, right? Then you'd include that here, for example, because you would be creating a publisher of that message type. But in this case, our publisher that we want here is we want a publisher that will enable our robot to move. So we have to specify that we want the twist message, which is the message that is standardized, that is the standardized way in ROS2 of sending commands that will trigger movement in the XYZ direction, or trigger rotations in those respective axes as well, right? Okay, so what we are also doing is we are logging. So we are telling ourselves, right, because the whole purpose of logging is for us to keep track of what is going on. So we are also telling ourselves that our constructor is executed. So when this node is created, you get a obstacle avoider node started in the terminal, written in the terminal. We are using the standard logger in ROS2, right, the info logger, right? So this will just send messages that are pertaining to giving information, right? If you were going to implement like a warning logger, it would be slightly different. However, the format is the same. You maybe use a different one here. Maybe if you want a warn, you'd say _warn or _debug, right? But the idea is the same. You are setting yourself some kind of history that you can look through in case things don't go as planned, right? Then what we are doing next is we have this function here that we call stop. So the idea, if you remember from the previous classes, or if you managed to attend, right, so what we noticed in those previous classes was that every time you send a command velocity to your robot via some program, in our case we were using a program that publishes to the command vel topic, or fastbot /command vel, right? We realized that after we pressed Ctrl+C or terminated the execution of our program, the robot continued moving, right? And if you remember correctly, I mentioned something along the lines that ROS2, let me say, messages, nodes, they latch onto the previous message that was sent to them, right? So if you have got a command vel publisher that last sent a message that was telling the robot to move forward at 0.1 meters per second, for example, right? That robot is going to keep moving at 0.1 meters per second, even though that node is terminated, right? So the idea of having inserted this here is to allow us to send the final message. So I will show you how that is happening as we go on, but it is to allow us to publish a final message with zero velocities in all directions and zero angular velocities in all axes when we have pressed Control C to stop the execution of our node, right? And this function that we call stop is going to be very useful in that case. And you can see that when we declare our twist message, first we declare it, then we populate its different fields with zeros everywhere, because we're saying when everything else is done and the user has pressed Control Control C, you must publish this as the final message so that the robot stops, right? Okay. And we're also logging some information to tell ourselves that, okay, we are publishing a stop message and then shutting the node right down. And then there is publishing happening here, right? So this is probably the first place where you see a publisher working, right? So remember, it was initialized here in the constructor, and we call it velocity publisher. And what we are doing here is we're just calling publish by using our dereferencing and accessing the member function that is called publish, right? And then passing it the message that we want to publish, right? So remember, this message is stop message, and we've filled it with these things. That's why you see there's stop message dot linear dot x equal to 0 all the way down to until 06 and fields have been populated. All right, so that's the message we're publishing here. So let's go down a bit more, right? So we see here now we have used a access modifier that we call private. So in C++, everything that is in a class is considered to be private. However, we still call this private for the sake of being explicit, so that everyone knows that we actually want to keep these methods for this class only, not for any other class that we inherit from it, or for any other usage outside the scope of the class itself, right? That is C++ detail. However, it's important to mention it here why we're doing it. Okay, so this one is quite big because it's doing a lot of things. It is the one function that will enable us to implement the naive obstacle avoider behavior that we want. However, remember I said the subscribing is being done in the same scan callback, right? So there are a lot of details that we would want to speak about with regards to this function, so that we understand why the best practices encourage us to do it slightly different than the way it's implemented here. It is possible, however, it would have made our code very long, so no worries. What's good is to understand. Okay, so I haven't explained the detail here because I want to come back to it later. So let's go on to this other final one, right? So get side distant. This is a different function, but this function returns a minimum distance. So it's the function that's responsible for giving us information about whether the bot should keep going forward, or should also give us information about whether we should turn, right, depending on where the minimum distance is, right? So if the minimum distance is on the left, you want the robot to avoid the left side because there's an obstacle there, right? So this function is responsible for processing I wouldn't want to say processing, but it's like the brain that will enable obstacle avoidance behavior by returning the right direction to avoid, for example. Let's say that, right? And then, so we're going to look into a bit more detail about those things later. However, what I think is most important is this, because this is where the whole mixing of publishers and subscribers is happening, right? So let me just Control C to eliminate that. So what I want you to understand in the deepest sense of the matter as far as ROS2 is concerned is that when you have a publisher that's running in a callback like this, right, it is a complex situation, it is very messy. It might work for us right now, right? That's the point. We want to understand it will work, but however, why I'm saying it's not considered best practice, it is because this scan callback here, because it is a callback, it is triggered every time new messages arrive, right? So every time new LaserScan messages arrive, right, that's when it is triggered to act, right? So it doesn't. Let's say we have our publisher for this LaserScan message, right, not running at a constant rate, so it's not publishing every in a predictable manner where we're saying every 10 milliseconds we're receiving a message, right? It might be working in that way, like if the system is working well enough. However, because it's dependent on that, it is very difficult for us to control a robot in a predictable manner, because the one publisher that is the most important, right, that is most important in relations to being able to stop the robot, making it move forward or making it move backward, is very much dependent on whether the callback itself executes, right? That's why we're saying, as we get into more detail about this, there is what is called a timer. What a timer will do is it will publish a command velocity at a regular frequency, whether LiDAR data comes in or doesn't, right? So it will keep publishing if it realizes that. So you could implement that timer that calls your publisher, right? You could implement it in such a way that if it doesn't receive LiDAR messages for longer than 10, 20, 50 milliseconds, then it will publish zero velocities to make sure the robot is safe, to make sure the robot does not collide. However, with regards to this kind of implementation though, the problem is that we do not have independent control of what of who is calling our publisher, right? It's like our publisher can only be called in the callback that subscribes to LaserScan messages, right? So this is where the intricacies and complications and the mess is coming from. However, it's a good thing to understand, so that we know that this can be made better. Okay. All right. So the rest of the logic that we have here, it's all about processing LiDAR messages. So if you see here, we have different indexes being checked, right? So if you would imagine that my front index is 0, right, and you're going counterclockwise, right? So if you're going counterclockwise, the left side would be your 90 degrees, and then the 270 would be your right. So if you look here, it says check the right side 90 degrees roughly, right? So what it means is that if you'd consider to the direction the robot is facing to be your 0, and you go clockwise in this case that we're talking about, right, and you go clockwise, once you have gone 90 degrees, right, that's what you consider to be your right side, right? So you have to do processing of the LiDAR ranges, right, with respect to that. So for us, what we're working with is we're working with a 450 LiDAR indexes. However, you can check them by doing a very, you could call it primitive computation, but it's very important to know how do you check the amount of indexes you've got. So if you open your terminal and you first check if you have the topics running, so if you go ROS2 topic list and you check the topics that are being published by your simulation, in this case not the real robot because you haven't connected yet, right, you will see that you have got fastboard 1 scan here, right? Here you've got fastboard 1 scan. So this is the one we are using, this is the one we're subscribing to. So if you type in ROS2 topic echo, right, because our simulation is running, so we should have something being published to this topic. So ROS2 topic echo, and you say /scan fastboard _1 then scan, right, and then you want it to echo only once, so that you don't get your terminal being filled by, hang on one sec. Okay, it does not appear to be published yet, so I think there's something that is happening to our simulation. I think this will require reloading, so let's reload it. Or we could connect to the real robot in the meantime, but let's finish the nitty-gritties of our package for now. So with regards to allowing your node to listen to Control C, there's an additional function that's going to work in conjunction with the function that we call stop, that I spoke about at the very top here, which is this one, right? And that function is the signal handler here. So give me one sec, this one here. So this is the function that will enable us to press Control C, because it uses a signal handler, so sigint, right? And that's why we have to include this header here to allow our node to terminate when you press Control C, right? And execute the right kind of things, that is publishing the zeros before terminating the node, right? So if you do not implement this, you can still press Control C and it will work, but we had to implement something specific because we want to determine what happens when we press Control C, right? So that is the purpose of that function. It enables us to do that and to control the behavior that happens after that, right? And that's why you see it here as well, right? All right, then we spin our node and we return a 0. So our main function returns 0 when everything is done and it is executed to completion successfully. Okay, so now let's do things that will allow us to run our node, and that means making modifications to creating a launch file, and also making modifications to the CMake list file to allow us to compile, then make our executables available. Okay, so if you open your terminal again, and let's clear this a bit. So in here we have our obstacle avoider.cpp implemented here. However, for launch files, you have to create them in a directory that's called a launch directory, right? And that launch directory is supposed to be within your package, right? It's supposed to be amongst the other things that are added to your package. So the way you would do that, the way you'd create a launch directory, is you'd make directory mkdir, right? And then you call that directory launch, right? Because standard practice, this is how the launch directory is named, or the directory that contains your launch file is named, right? You hit enter and then you list the contents. You realize you have that launch directory created, and you open it, you get into that, then you use the touch command as we have done earlier, and create our launch file in there. So our launch file is going to be called obstacle-avoider.launch.py. So let's open that. Let's open our terminal real quick, and then name our launch file here. So obstacle-avoider.launch.py, right? And then hit enter, then list the contents. You realize you have that as well created, and we're going to do the same thing that we did for the CPP file. We're going to open our launch file and add details to it, right? And add the code to it. So if we check our notebook, this is what will be contained in our launch file. So we're going to break this down a bit so we understand what we are doing. So open your IDE and then Control V again. So here we are naming our package. So this is generate launch file description. So it's a function that will return our node launch file, right? It will create like a handle that will allow us to launch our node, right? But to do that, it needs to know what is the name of the package in which this node is found, what is the name of the node itself, right? Or the executable that will be, let's just call it the binary file, right? For example, so the executable is called, or the binary file is called obstacle-avoider_node, right? And then the output to the screen, right? So it returns stuff to the console, something like that, right? Okay, so let's go on and make the necessary modifications to the CMake list file so that we can be able to compile our code, right? So if we go to our notebook, there are three things that we need to do to allow ourselves to be able to compile our executable and our launch files and make them available for execution, or make them available for calling them via ROS2 launch, for example, right, or ROS2 run, right? So if you open the notebook, this, let's copy this first before we speak about it, and we put it in the CMake list file, right? So if you open your IDE again and then you go here, so you have to put it above the amend package here, this statement here, otherwise your program will not compile, right? So okay, what we are doing, I think these are the three most important things you need to know when you are doing when you're compiling your packages and allowing them to run via a launch file, right? So what is important for all nodes, whether you're going to be creating them, whether you're going to be running them using ROS2 launch, or you're going to be, hang on one sec, or you're going to be running them using ROS2 run, it's very important for you to declare what the executable will be called, right? So the executable, remember I said, can also be called the binary file, right? So in this case, we are saying to the compiler, the binary file that will be made from this source file here that is found in the SRC directory and is called obstacle avoider.cpp will be compiled and given the name obstacle avoider node, right? That's why you see in the launch file we use that same name here for executable. That name must match this name that you find in the launch file, this one must match the one that the binary is called, or that will be given to the executable that will be produced after the compiler is compiled, right? And then here what we're doing is amend target dependencies. We are linking, right? So linking is the process of joining the libraries that will work with our executable, right? So our executable is called obstacle avoider node, obstacle avoider node, and it requires RC or CPP library to run. It requires geometry messages to run. It requires sensor messages to run, right? So the linker has to pull these things together and make them available for our binary to use, right? Because they are things that are very much needed for it to run correctly, right? And then what we're doing after that is we are installing our obstacle avoider node, right? So what we're doing is we are making it available for execution, right? So we are making it available in the library, in the lib file that's found in the shared directory. So if you open your build file and you open the package, you should see that you've got a, where is it now? Right, should be this one here, if I'm correct. Yep, here. So you have got that executable available in that package, right? So you are trying to tell the compiler that put this executable in this directory so that it's found for available for execution, right? So when you call ROS2 launch or when you call ROS2 run, it's available there, right? You have to install it. If you don't, you cannot call it that way. You cannot run it in such a manner. You'd have to look for it explicitly, and then maybe, because it's a C++ package, then call / the name of the node to run, right? But there are complications related to that. I just wanted you to know that the standard practice is you need to install it to be able to run it, and then you also need to install the launch files so that they can run, and also that you can call ROS2 launch the obstacle avoider.launch.py, right? Okay, so let's compile our code and run it. I hope our simulation is loaded, because okay, no worries. Okay, let's compile it. And so to compile, you have to go back to the root workspace directory, right? So all ROS2 package, despite that your name might be something underscore workspace, you always need to compile in there. If you compile elsewhere, that will lead to trouble. So standard practice, you have to compile in that workspace. That's why we are navigating to that first before calling cocon build, right? So here we're going to do cd and then go to that directory. So if you want to specify the path, the absolutely to say go to this path, you can use the tilde, right? It will specify, it will allow you to go to it directly, other than having to press cd dot like this for 3 times to get to the workspace directory, right? So the same thing applies if you're going forward. If you do ROS2 workspace and then src, it will work just like normal, because you are saying you're giving it an absolute path. Okay, so we are in here. This is where we're supposed to call cocon build. So let's do that. So in this case, we specify that we want to build obstacle avoidance package only, right? Because we've built the others already. Or if you haven't, you can just call cocon without having to specify, without having to add this flag that says packages select, right? So in some cases, you have so many build files, you have a lot of packages that you've already built, and it doesn't help you to rebuild them, right? So what you do is you use the package select option or flag to say build this package only. This is the one that I want you to build. You're telling cocon that, right? So in this case, we're gonna do that and hit enter. Then our package will compile, and then after it compiles, we have to source, right? So sourcing is like telling your terminal or your base terminal, this terminal that you're running in, this 518 terminal, you're telling it that you can find the new executables, or you're telling it resource or rerun the setup.bash so that you can be able to see the new executables that have been made available, right? That's what you're doing. So we have to source it. If we do not source it, right, our 518 terminal here does not know that there is a new executable that is called obstacle avoider.launch.py that's available for me to execute, or that's available to be called using the ROS2 launch something, right? So you have to source it to allow that to happen, to allow it to be found when you call that ROS2 launch obstacle avoider.launch.py, right? So source install setup.bash, right? And then you can now go ahead and launch your obstacle avoider.launch.py. However, for us in this case, I think we have a bit of an issue. If your simulation does not load right now, we will have to switch to the real robot. So let's try that real quick to see if our code will run correctly and see if we will need to make some modifications. So if you would allow me to close this a bit, and let's see if we can connect it. So I think we have to scroll right. So we want to connect to this one, and we'll try to run it there. So see if it works. My assumption is that we need to modify a few things to allow our code to run on the real robot, because what is doable in simulation is not, if not always, transferable to the real environment, because there are so many other things that simulation does not take into account, right? Friction, for example, it's a very simple thing that is very much affecting to how our robots perceive the environment, or how they are driven by the codes that we would have developed for them, right? So let's wait for this to load, and then we can give it a shot. Okay. Give me 1 sec. Okay, I'm not sure if the bot is available, so Let me check real quick. Alright, let's just refresh and see. Let me disconnect just one. Alright, so if our simulation would have loaded quick enough for us, the kind of behavior that we should see is something like this. So let's wait for this GIF, to start again, right? So what we should see is something like this, where the robot will be able to avoid the wall and move forward, move backwards, right? However, there's something that happens right here towards the end of the recording, right? You see the robot struggling to get out of that zone. These are some of the improvements that would need to be done to the code, right? Because right now the robot cannot get itself out of the stuck situation, right there it's getting confused whether it should go left or right, because it's getting equal amounts of minimum distance, right? So the left is saying the minimum distance has been reached, this one is saying the minimum distance has been reached, so it's stuck. It cannot go forward, go backwards, rotate out. Every time it rotates, it does not rotate enough to get itself out of that place. So it's a good thing to understand, or to at least know the limitations of our code, and this is part of that. It's part of trying to understand some of the nuances of what happens when you implement certain behaviors and you do not have knowledge about some other type of situations that your robot might get into. That's why it's important to at least do tests, or to think about all the broad cases that your robot might end up find itself in, right, and create backups for them, right? However, sometimes it's very difficult to be exhaustive, so you only get to see these things in action. So in cases like this, you must have a backup strategy that is very primitive but allows your robot to get out of that state. For example, in this case, we could have maybe had a behavior where if it checks 4 times the left and the right and it keeps getting the same value, what it will do is stop, do a 180-degree rotation, then check again, right? So it's good things to know. Alright, so let's wait a bit to see if we can at least do some tests on the real robot. Otherwise, we might have to hang on to what we've got for now. Let's try again to connect. So for okay, let's wait for it first. I think if it does work, we can see. Alright, I think this is not getting us much unless we find a way of intervening real quick. So let's disconnect and then we can try later. Alright, so let's maybe give it a couple of minutes, but I don't see this loading anytime soon. Alright, so I think let's wrap it up for now. We can try and find a way of maybe recording the demo so that you can have some form of know-how of what kind of behavior to expect, and then we can maybe use this as a platform for another open class where we get into more detail about what can be done given the things that we would have experienced after we run this on our real robot, for example. But for now, let's call it a wrap, and then we can meet in the next open class. So I wish you all the best, and bye bye.